Hi! Today we're going to learn about the comparison theorem in calculus. Let's say we have a problem like this. Are they convergent or divergent? And we're talking about A, the integral from 5 to infinity of 1 over x minus 2 dx, and B, the integral from 5 to infinity of 1 over x cubed plus 3 dx. Before we get started, let's first look at a graph and try and understand what the comparison theorem is. So let's say we just had a standard x and y axis graph. So this is the Cartesian plane, and let's say we had some function like this, and it kept going this way and kept going in this pattern. So we know that as this function approached infinity, the area under its curve would also be infinity, or divergent. So this area would be infinity, or divergent. Now, let's say we had a function that was bigger than this, from 0 to infinity. So it can be smaller until here, but as soon as it hits 0 or before that, it has to be bigger than this function, and all the way to infinity, this function must be greater than the function that we have here. So let's say this original function was f of x. This new function, let's say, is now g of x. So this g of x is greater than f of x on the interval from open parentheses 0, or close parentheses 0. In this case, we're going from 0 to infinity, so it has to be greater than f of x from 0 to the infinity for the other bound of the interval. Now if we do that, then we know that this area is the same as this area under the first curve f of x plus the area between these two functions. Now, if the area under the first curve is infinity from 0 to infinity, and we're just adding more area to that, then that means that the total area is also infinity. So this represents the total area. But what is the total area? Well, this total area would be this area plus this area, which we can also see is the area under the curve g of x from 0 to infinity, because g of x has the area under the curve of this. So g of x has a total area under the curve. And so for adding infinity plus infinity, that means that we get a divergent integral. So this is divergent. There's an infinite area under the curve because it's greater than a curve that we know already has an infinite area, or is divergent. So this is how we know whether a function is divergent. Well, how do we know whether a function is convergent? Well, take a moment to think about it while I erase this. So how do we figure out if the function is convergent? Well, that would be just the exact opposite. So we once again have our Cartesian plane, which is, by the way, just an x and y axis graph. And let's say this time we have a function f of x. And let's say we want to find the area under this curve from 0 to infinity. And let's say that we know this area under the curve is a finite area. So that means that it comes out to a particular number, like 2 or e or pi or something. So this is a finite area under the curve. So what it means is that the area under the curve comes closer and closer to a number. So the limit of the area under the curve is a number. Now, let's say that we had another such function, g of x. So this is, once again, f of x. But this time, g of x must be less than or equal to f of x from the area that we're trying to find. So from, in this case, 0 to infinity. So from 0 to infinity, it's less than f of x. Just imagine that this portion is less than f of x. So it's less than f of x. And greater than this x-axis over here, so that it doesn't go below the x-axis. Well, if we know that the area under f of x, and let's name this one g of x. So if we know the area under the curve for f of x, and we know that this is a finite area, it doesn't matter what it is, we know that this is finite. So let's say that this value is a constant c. This area under the curve is a constant c. Then that means that the area under g of x is equal to this total area under the curve minus the area between g of x and f of x. So basically the exact opposite as what was in finding out if they were divergent example. So basically the area under the curve of g of x is equal to the total area we named c minus this area between g of x and f of x. Now if we have a finite area minus some area, then that means that we also get a finite area. And we know that this area is not infinite or is not divergent because it's less than the finite area. That means it also has to be finite. So that means that this area also has to be finite because we're subtracting a finite value from another finite value, and that means that we have to get a finite value. So that means that the area under the curve for g of x from 0 to infinity is convergent or finite or convergent. So let's apply that to these two problems, but let's do it without graphing. So we know what the comparison theorem is, but we don't know how to use it now. So let's try and see if we can figure out how to use the comparison theorem. Now, we know that we don't have a graph anymore. So how do we say the comparison theorem, or how do we identify the comparison theorem? So we say that for the convergency one, or the second example that we looked at, if g of x is greater than or equal to 0 for all x on this, so if the integral for g of x from a to b is greater than or equal to 0. So basically what this is saying, or what this means, is that all g of x has to do is g of x has to be greater than or equal to 0 from a to b, because then our area will be greater than or equal to 0 from a to b. So if g of x is less than or equal to if the integral, from a to b of g of x is less than or equal to 0, or is greater than or equal to 0, and is less than or equal to the integral from a to b of f of x, and, once again, another and, we know that this is convergent, so I'm just going to say CON for short, and we know that this integral from a to b of f of x is convergent, then that means that this integral is also convergent. So, the three conditions are that this integral has to be greater than 0, so basically g of x has to be greater than 0 on the interval from a to b. It has to be less than f of x from the interval from a to b, and the integral from a to b of f of x has to be convergent. And if all three of those conditions are met, then the integral from a to b of g of x is also convergent. Now for the divergency one, we have if g of x, or the integral of g of x, from a to b is greater than integral from a to b of f of x dx. Sorry, there should be a dx here. And one there. And one there. And this integral is greater than or equal to 0. So remember that if these are negative, then it gets flipped around. So in that divergency one, it only works because g of x, when g of x was greater than f of x, because it was positive. Now if it was negative, then g of x would have to be under f of x, and therefore it would have to be less than or equal to f of x. So we just have to switch them. Like when multiplying by a -1, the signs flip. So, if these conditions are met, and the integral from a to b of f of x dx is divergent, I'm going to say DIV for short, then this means that the integral from a to b of g of x dx is also divergent. So take a moment to memorize these before we jump into problem A and problem B. So, let's do that. So for problem A, can you think of a function that is less than or greater than 1 over x minus 2? Well, there's one particular function that comes to mind. So usually we want to think of parent functions because parent functions are the easier ones to calculate integrals of. Now the one parent function that comes to mind here is 1 over x. 1 over x. Now is 1 over x less than or greater than 1 over x minus 2? Well, here we have 1 over x minus 2. That means that the denominator is smaller. And if the denominator is smaller, then that means that the value is bigger. So that means that 1 over x is less than or equal to, and this is for positive values, or values not actually positive, but when the denominator is positive. So this is basically for values that are greater than 2. As you can see, our integral is from 5 to infinity, so all those values are greater than 2. So that means that the integral from 5 to infinity, 1 over x dx, is greater than the integral from 5 to infinity, or is less than, sorry, less than the integral from 5 to infinity over, or from 5 to infinity of 1 over x minus 2. And as we know, these would all be greater than 0 because the denominator is positive and the numerator is positive. So, technically this greater than or equal to 0 has to be on this side, but for our purpose it doesn't really matter. So, as you can see, if these conditions are met, and if this integral is divergent, then that means that this integral is also divergent. But do we know whether this is divergent? Well, let's find that out. So the integral of 1 over x is the natural log of x. Now we have to evaluate this. Let's move this down. It's the natural log of x evaluated at infinity and 5. So this would be equal to the natural log of infinity minus the natural log of 5, which is equal to infinity minus the natural log of 5, which is infinity. And we know that we cannot put infinity down for an answer because we don't know what infinity is, and that means that this is divergent. So the answer is, because we know that this is divergent, and these conditions are all met, that means that this function is also divergent according to, or this integral is also divergent according to the comparison theorem. So take a moment to go over this, and then we'll move on to problem B. So this integral is divergent. So let's write that down here. Divergent. Now let's move on to problem B. Is there any function that we know that's greater than or less than this function here? Well, once again, we want to think of a parent function. And the parent function that comes to mind is 1 over x cubed. Now, is 1 over x cubed greater than or less than 1 over x cubed plus 3? Well, here, as we can see, the denominator is bigger. That means that the whole value will have to be smaller. And so that means that 1 over x cubed is greater than 1 over x cubed plus 3. So 1 over x cubed is greater than 1 over x cubed plus 3. Now we have to make sure that it's greater than for all the values on this interval here. And that's true because all of these values make both of these positive, and therefore this inequality will hold true. So that means that this integral from 5 to infinity and dx is less than or equal to the integral from 5 to infinity of 1 over x cubed dx. And we have to make sure once again that they're all greater than or equal to 0. Forgot that in the beginning. So, as you can see, all of these will be greater than or equal to 0 because this interval does not include anything that includes 3 or is less than 3. It's just from 5 to infinity, which we know are both above 3. All the values in here are greater than 3. So now, according to the comparison theorem, if all of these inequalities are true, which they are, and this is convergent, then that means that this is also convergent. So let's figure out whether this is convergent. We have the integral from 5 to infinity of 1 over x cubed. So that's the integral from 5 to infinity of x to the negative third power, which is equal to negative 3 over x squared. So negative 3 over x squared evaluated at 5 and infinity, which is equal to negative 3 over infinity squared minus 3 over 25, which would be equal to, now we know that negative 3 over a really, really big number becomes 0. So you get 0 minus 3 over 25, which is just equal to negative 3 over 25, which, because this is a finite value, that means that this integral is convergent. So convergent. And because all of these inequalities hold true and this is convergent, that means that this is also convergent. So the answer to problem B is convergent. Today we learned about the comparison theorem in calculus. Thank you for watching this video.